Okay, so we are going to look at the atomic structure, and here you can look at the history. You can look at the history of how these the actual structure of atom was discovered on your own. But let's look at one of the basic things here is that Niels Bohr, he came up with the structure of atom, and he said, and he actually studied the hydrogen atom, and he found that nucleus is in the center, and this nucleus contains protons, which are small particles positively charged. Okay, and the mass of the proton is one. The relative mass is actually the mass in kilograms. Let's just write that down. The mass in kilograms is 1.673 into 10 to the power negative 27. So 1.673 into 10 to the power negative 27 kilograms. Okay, so that has been verified through not just the experiments, but also through math. Next comes the neutrons are also present in the nucleus, and these neutrons have no charge, and their mass is 1.67, and it's slightly bigger into 10 to the power negative 27 kilograms. Okay, so slightly bigger. And this nucleus forms the main bulk of the atom. So the atomic weight that you see, the weight of the nucleus is this here because of the center. All around the nucleus is these energy levels. These energy levels, in the past, they had equated the structure of atom to that of the solar system. So an older term you will see is the orbits. Okay, you will also see orbits. So anyways, so now a more advanced term is the shells or the energy levels. So these shells, energy levels. So these energy levels or the shells is where we are going to find the electrons. So electrons are negatively charged, and these electrons, I'm going to pull this here. So these electrons have a negative charge, and they are, the mass is 9.109 into 10 to the power negative 31 kilograms. So like really, really small. So in other words, if you have the mass of, the mass of protons equal to 1 atomic mass unit, the mass of neutron is going to be a little bit more than 1 atomic mass units. Okay, then the mass of electrons is 0.00055 atomic mass units. So like really, really small. Okay, so that's the basic thing. Now, what else do we know about these electrons? So electrons are existing as electrons. First of all, are always in high energy, they're always moving. So they have kinetic energy. Kinetic energy is the energy of motion. So kinetic energy is the energy of motion, and because of which these electrons are moving all around the nucleus. How are they moving? They are spinning on their axis. Okay, they are spinning on their axis, and they're also revolving, just like the earth revolves around the sun. So these electrons are also revolving around the nucleus, okay, around the nucleus. But they are in their very specific energy levels around the nucleus. Now, this is a very basic thing. Besides that, a little bit more advanced, and that is that the electrons can exist as waves, and these electrons can exist as particles. So the reality is that at one point of time, it is hard to determine whether the electron is existing as a wave or whether the electron is existing as a particle at one point of time. So we don't know. So it's hard to determine. So that is why, there is going to be, this uncertainty principle, uncertainty principle. And which is like we don't know whether they are existing as waves, but we know for sure that the probability of finding the electrons is definitely is in the energy levels. Okay, is definitely in the energy levels. So that we are sure. Now, when we talk about these energy levels, we know that these energy levels have, like we talk about energy, so that means they're quantized. Quantized energy levels means that the energy levels have a value. So the energy levels are quantized. Now, what does that mean, quantized? Now, okay, here's a very interesting part. They discovered these energy levels and they found, they did all these experiments and they found that these energy levels, they have a value, and this value they determined through light. So they had studied light, and in that the electromagnetic radiations, light is a part of that. And so the light has a frequency, light has a waves, and there is a certain energy associated with a specific color of light. And we know these lights is made up of 7 colors: violet, indigo, blue, green, yellow, orange, and red. All these 7 colors have a very specific amount of energy. So using those figures and then all these black body radiation experiments, and we are not going to go much detail into the historical part, but just so you know that the energy levels of atoms were quantized, or in other words, the value to that energy was given using the experiments in which light was, was a factor. And so the colors of the light equated to the energy levels and so forth. So Chem 1A has more details on that, but for beginning level courses or introductory courses, this is suffice to say that. Okay, now we are going to now look at the first of all, the mass number and the atomic number. So what is a mass number? Mass number and the atomic number. So atomic number is the number of protons, and this also is equal to, for a neutral atom, it is also the number of electrons. What is a mass number? Mass number is the number of protons plus the number of neutrons. Okay, when these are combined together. But now, fine, this is one piece, this is another piece, and the third piece here is that how do you find the number of neutrons? The number of neutrons are determined when you take the mass number minus the atomic number. Okay, so here is the mass number minus the atomic number. Okay, so let's find this thing first. Let us say you are given, let us say chromium, for example. So this type of question can come on the exam. You have, let's say chromium. Now, different ways these can be written. It can be written like this, 50 and 24. Okay. This can also be written as chromium 50 and 24, and it all depends, in the books you will see this in different ways these are written, and it doesn't matter. It can also be written as 50 and 24, or this is also written in the publisher, sometimes write it as 50 and 24, and sometimes they also can write down chromium 50, or they can also write down chromium 24. It depends, what are we focusing on? If we are focusing on the mass, then yeah, it's okay to use this one. But if you're focusing on the mass atomic number, then you use that one. But other than that, any of these forms, as you see in all these different books, and again, it depends on, publishing and typing, all those scenarios, All of them are correct. Main thing here is that these numbers, as far as these numbers are there, that will relate to chromium, especially this mass number 24. So 24 is important. If it is 25, it's a different element altogether. If it is 23, it's a different element. If it is 25, then it is manganese. But if it is 23, then it is vanadium. So the identity of the atom changes. So as far as it's 24, we are okay. Okay, it's chromium. Okay, now let's look at this. So the type of question that can be asked, find the number of protons, find the number of electrons, find the number of neutrons, and tell what is the mass number and tell what is the atomic number. So these type of questions, you have to just do it. So the number of protons is, you guys tell me. Number
24.
of 24. Number 24. Of electrons, 24. Number of neutrons,
26.
Very good. So 50 minus 24, that is the mass number minus the atomic number. So it comes out to be 26. Very good. So that's protons, that's electrons, and that's neutrons. Now what is the mass number?
50.
50.
50.
Now, and the atomic number?
24.
24. Okay. So very good. So this type of question can be asked on the exams. Another thing that you have to notice now here is very interesting. If the mass number is, this mass number 50 is the number of protons plus the number of neutrons, plus, this is plus the number of neutrons, okay, which means 24 plus 26, and that equals to 50. Now that is an exact number, right? It's a very simple exact number. Very simple exact number, right? Then if you look in the periodic table, you're going to see that there is a decimal, and we see that there is like decimal points, and you know the answer, the chromium can have like chromium can have like a 52 point, what is it, 50 chromium is 52 point, sorry, chromium is,
It's 51 points.
yeah, say that again.
9961.
Yeah, every periodic table has a difference. You tell me that 50, which is that?
51.9961.
9961 atomic mass units. So this is one periodic table is showing that. Now the one that I have is showing 52.00 atomic mass units. Now that is my periodic table showing that. And let me just, for the sake of, let me just look into this one. Yeah, so another book is also showing 52.0. So every book, you know, so every periodic table is showing little discrepancy. So first of all, why is it not showing as an exact number? Why is there, you know, this thing? So there, the cause behind that is the isotopes and the abundance. So isotopes, iso means same. And P here, the way I do it is P is for protons. So same, so those elements that have same number of protons, but different number of neutrons. So those are called isotopes. Now here, let's look at this example of chromium once again. So here you have chromiums. The other isotopes of chromium are, fine, this is 24, I'm going to put it here, 24. This is chromium 24. This is chromium, I need more space, 1 second. So here is your chromium. Let's put 24 here. Chromium 24, and here's chromium 24 and chromium 24. As far as there are 24, that's chromium, and that's fine. But there is chromium 50, there's chromium 52, there's chromium 53, and there's chromium 54. So you see that somewhere we are we are seeing that yes, the atomic numbers, all of them. Now let's write this down. Atomic numbers, mass numbers, and then the number of protons, number of electrons, and the number of neutrons. Okay, so let's start doing this. So we see that for the chromium, the atomic numbers, all of them will have the same atomic number. 24 here, 24 this one is 24, and this one is 24. Okay, so we are fine with the atomic numbers. Mass numbers are different. This guy has 50, this guy has 52, this one has 53, and this one has 54. So you see the weight of the atoms is changing. So how many protons are there? All of them will have the number of protons, and the neutrons are the same. Sorry, the protons and the electrons are the same. So 24 protons for neutral atoms, 24 electrons. So that's all same. But the number of neutrons is going to be different. Now what is that? 50 minus 24. This is 52. So 50 minus 24, let me write it with a different. So here, 50 minus 24. This one is 52 minus 24. This one is 53 minus 24. And this one is 54 minus 24. So what do you get? 50 minus 24, we already did 26. So 26 neutrons here. 52 minus 52 minus 24 is?
28.
28, very good, 28 neutrons. 53 minus 24 is? 29. And 54 minus 24 is? 30 neutrons. So you see, as the number of neutrons increase, the weight of the atom changes, but the identity, the physical properties, the chemical properties, nothing changes. It's just the weight changes. Now, we have to factor in all this, we have to factor in all these. Because see, here's the thing. There's going to be one isotope that is going to be more abundant, which is found in nature in large number, right? So that's fine. But then there are other isotopes also, the other varieties of these elements, which are found in trace amounts, small amounts, and they may be radioactive, they are, unstable, and they are in very tiny amount, they are found in nature. But we can't overlook that. So because matter, right? We cannot play around with the matter. So anyways, so we have to factor in all these different types of chromium that are found in nature, even if it's in a small trace amount, and that's called the abundance factor. So one is the which isotope is more abundant, take that, plus the isotopes, all these other isotopes which are less abundant. And less abundance means like how much is it available in the atmosphere? So you on this earth, so you take that and then you add those. So let us say one more example here. One more example here is that of, let's say, chlorine. And so this is again an exam question. So here is these two isotopes of chlorine, and they're saying calculate. So the question is calculate the atomic mass. Calculate the atomic mass of these isotopes. And what are those isotopes? And here is your chlorine. Okay, and here's chlorine 35 and 17. And that's fine. And this is chlorine 37 and 17. So the name of the element is chlorine. It's a gas, fine. So one of them is chlorine 35. The other one is chlorine 37. And usually, it is the one that is less abundant is the one that's unstable and a small amount, but still we need to bring it into so here's the masses in atomic mass units. So here is this 34.97, and we, round it up to 35. But reality is that chlorine, that is the actual mass of this. Then the other one is 36.97. Okay, now here's another thing. Significant figures, you need to bring those rules regarding the significant figures, because we are kind of, it's like a measurement. It's like, I mean, it's a calculation, but it's, we need to be exact. Okay, so here, times. Now this guy is found, next is the abundance factor. Abundance is how much of it is present in nature, and that is in percentage. So here, this one, chlorine 35 is 75.76%, and 75.76% means 75.76 divided by 100. The other one is 24.24%. 24.24 divided by 100. Okay. All right. So 34.97 times 75 divided by 100 gives you 26.49 atomic mass unit. So this is the contribution coming from chlorine 35. Next one is 8.962 atomic mass unit. That is coming from the chlorine 37. And then you're going to add these up. Add these up. So what we write in the periodic tables, every single element you see in the periodic table has a, the mass is in a decimal. So when it's in a decimal form, that means that's average. We have taken the average weight of the isotopes. So combined together, okay? So here, this one comes out to be 35.45 atomic mass units. All right, so here you see this, look at the significant figures. This is, let me make this smaller. Okay, so this is 4 significant figures. 4 significant figures. This is 4 significant figures. This is 4 significant figures. Okay, so when you do all this math and divide, so for some reason, this one is 4 significant figures. And let's say this is 5, this is 5 significant figures. So now we do not round up or round down in between, so do not round up here. Like you keep this number as it is, you keep this number as it is, and then this one is, whatever. So don't round up, do not round up here, do not round up here. So just look at the final answer now. Final answer, we need 4 significant figures. So those are that should be, that's the number that usually goes on the periodic table, but sometimes, these are commercially made. So chlorine is 35.45. If you look in the periodic table, this is 35.45 is the one you will see. Okay. So this is one thing, very basic things about, the atomic numbers and the atomic weights and the isotopes and how many protons, neutrons. So another very interesting one here, for example, I'll show you for hydrogen, how they have made the isotopes of hydrogen. So here are your isotopes. How do they look like? Isotopes of hydrogen. Okay, hydrogen. So how do they look like? Here is the hydrogen, 1 proton, and that's a mass number. And the, give me 1 minute. Okay, here, hydrogen, 1 proton and 1 electron. And so basically, what was it? Yeah. The mass number is also 1. So that's for the hydrogen. So this means this hydrogen will have 1 proton in the middle and 1 electron is around it. This is commonly. So 1 proton and 1 electron. So this is a common hydrogen, more abundant are normal hydrogen. Okay, let's look at the next one, which is hydrogen which has like one proton, and it has two like the mass. So how do I say this? So here, let's just do this here. The mass number is 1 and the atomic number is 1. Okay, in this case, you have the mass number is 2, but the atomic number is 1. Okay, so here, how does this mean? So here is this electron. Okay, no, sorry, proton, and all around is fine, 1 electron, right? So this is one proton, 1 electron, and there is 1 additional neutron. So mass number is 1 proton plus 1 neutron. So excuse me. So this is 1 neutron. And here I'm going to show the neutron in a different color. So this is called the deuterium. Deuterium, D-E-U-T-E-R-I-U-M. Okay, so this is one isotope. This is another one, and then comes the third one, which is hydrogen 1 and 3. So here we will have 1 proton outside, 1 electron. You see how the number of protons and electrons are the same, but the number of neutrons here are 2. Okay, so here heavier, bigger. So now we will see the mass number is 3. Atomic number is 1. Actually, this number. Atomic number 1 and mass number is 3. So that means there is 1 proton plus 2 neutrons. Okay, and then there is 1 proton and 1 electron. Okay, and this, the name of this is called tritium, T-R-I-T-I-U-M. Okay, so so mass is just, yeah, so this is the mass number together, and this is the mass number together here. Okay, so this is how, we see it, and there are many others, but this is how this looks like. In other words, the isotopes, how they look like. Okay, so these type of questions you have in the periodic table in the book regarding the masses. Then comes the arrangement of electrons, which is basically the electronic configuration. And for that, I made a very specific video for that. So we're going to just review that. Okay, so I'm going to stop this now. And